Okay, hey everyone. Today we're going to be talking about neural language models. So continuing the topic from the previous lecture of language modeling, but now extending it to a more complex class of models that essentially converts the problem from counting and then normalizing, as we saw with n-gram models, to learning a model to predict the next word given a representation of the prefix. And this is in many ways a more powerful formulation, especially for the transfer learning paradigm that we've discussed in the first two lectures. Okay, so before we get into today's topic, I wanted to go over some of the questions that came up from last time. So we had a question about the pass-fail policy, which for graduate students is technically satisfactory or unsatisfactory. We are going to allow you to decide whether you want to switch from a letter grade to pass-fail at any point between now until the final report deadline, which is December 4th. So if you want to take this class pass-fail, you should send an email to the instructor's account with your request, and also make sure to send us a reminder email at the end of the semester. Oftentimes these emails might get lost. If someone doesn't note it down, then you want to make sure to have reminded us of it, because the end of semester can get kind of hectic. Okay, so other stuff, your homework 0 is due this Friday. Again, if you haven't started it and you're a little iffy on your programming or math background, I would encourage you to start early. And finally, your final project groups, the identity of the members must be formed by this Friday. Otherwise, we'll do it for you. So I guess by now you've seen the Piazza post by the TA suggesting that these group assignments won't be done completely randomly if you haven't specified your group. Instead, we've collected a bunch of information from you regarding, your interests, your time zone, etc., and we'll do our best to make reasonable groups that are, roughly within the same time zone and also sharing common research interests. So it's not a huge deal if you're unable to find a group, but of course, if you want to pick your own group members, make sure to submit the form by this Friday. All right, so let's launch into today's topic. So just as a quick refresher, language models are basically trying to measure this joint probability of a given sequence of words. So this could be a sentence, a phrase, a large document, any piece of text. And last time we looked at how we can factorize this joint probability as a product of multiple conditional probabilities. So any model that's able to compute a conditional probability of a word given some number of words as a prefix is also able to compute this joint probability of a sequence via the chain rule, which we went over last time. Okay. And last time we looked at n-gram models, which are, again, very simple methods of estimating these conditional probabilities. So in essence, you have a training data set of a bunch of text. And for any given prefix that occurs in that training data, you're going to count up first how many times that prefix occurs, and then how many times a particular word occurs after that prefix. So it's basically this count and then normalize style way of estimating these conditional probabilities. And this is an example of maximum likelihood estimation. So you're maximizing these probabilities on a training data set. Okay, so before we get into neural language models, I want to go over some of the issues with n-gram models that motivates more complex models. So the first issue is this problem of sparsity, right? So we looked at this briefly last time, but let's say this numerator here, the count of students open their W sub j, is 0 for a particular W sub j. That means this whole probability, this whole conditional probability is going to be 0. And that also means that if we see at test time, any documents or sentences that contain this phrase, students open their W sub J, the probability of that whole piece of text is going to be 0. So this is obviously undesirable. And we discussed a way of getting around this, which is called smoothing, right? So the intuition behind this is that for every count that I actually observe in my training data, I'm going to steal some value from each of those counts and assign it to counts that that are 0, right? So if students open their W sub J is 0 for a particular W sub J, I might add a small value from the observed counts to this unobserved count, such that at test time, the probability of some document containing this phrase, students open their W sub J, is no longer 0. Okay, there's a second problem, right? What if the entire prefix doesn't appear in my training data? So students open there. In that case, the denominator is 0, which is of course bad. And so traditionally, language modeling in n-gram models get around this using a method called backoff. So if students open there doesn't exist, then I will back off to the bigram students opened. If that still hasn't been observed in my data, I'll back off to just students. So at every point, you're kind of getting a worse estimate, right? Because you're ignoring a word because you had no data for it in your training data set. But at the end of the day, this lets you get around the problem of unobserved prefixes. But both of these are kind of hacky methods, right? And we would love for a model to not have to apply these techniques to a language model to get around this problem of 0 counts in the numerator and denominator. Another issue is storage. So remember when we were looking at that restaurant review data set, we were just looking at a bigram table, but we had to form this table, right, of all of the prefixes and then all of the words that follow that prefix, right? And then we counted up, how many times did this prefix, this word occur together, and then we normalized by the unigram probabilities of the prefix, right? That was for a bigram model. But imagine now we're doing a 7-gram model, right? So now the rows of this table, right, all the prefixes, I now have, V to the N order rows, right? So I have a huge number of rows, and every time I add one more word to my prefix, so if I go from a bigram model to a trigram model to a 4-gram model to a 5-gram model, the size of this table grows exponentially. So this really prevents me from estimating huge order n-gram models, even with large data sets, right? Because I just will run out of memory, and the sparsity problems that we discussed before with these 0 counts become much greater in settings where you have larger n. So if you remember the Shakespeare example that we went over in the last lecture, with a 4-gram model, like 99.9% of the counts in the table were 0. So you can imagine smoothing and back off, etc., become much more important in these kinds of settings. So we have basically 2 key issues so far, right? One is the sparsity issues, a lot of 0 counts, and the other is memory issues. And a third issue, which is kind of related to both of these things, is that in n-gram models, all words and prefixes are treated independently, right? So let's look at our prefix students open there, right? The one we've been looking at to this point. So I count up all occurrences of this particular prefix and the words that follow, but this has not influenced my count of pupils open there, right, which is a kind of paraphrase of this initial phrase. Scholars open there, right? It's maybe not the exact same semantics, but it's very close. Undergrads open there, or students turn the pages of there, or students attentively peruse there, right? You can imagine, they don't have to be identical semantically, but all of these things are roughly talking about the same topics and the same action. And it really makes sense that if we have a model, it should be able to share information across these semantically similar, or in some cases, almost identical paraphrases of these prefixes. So I guess at this point, we'll go over two ways of representing words. And first, we'll start with the representation method used by n-gram models and many other bag-of-words style models. So for example, the naive Bayes classifier, which we're not covering in this class, also relies on this assumption. And commonly when you're setting up a logistic regression model for NLP, you're going to also rely on this bag-of-words assumption. And at the core, it's very simple. I'm going to represent every word as a vector of zeros with a single one that corresponds to the index of that word. So if I had, let's say, this toy vocabulary of 6 words, I hate, love, the movie, film, I might represent the word movie as 00010, where this 5th dimension here corresponds to the word movie. And I might represent film as 00001, where this last dimension, if it's 1, that means the word is film. And so I might represent a phrase by adding these vectors together, right? So if I had the bigram movie film, which of course doesn't make any sense, but let's say I had it, I would get a vector of 00011. So this is essentially the way in which we're treating words in an n-gram model, but importantly, we're treating prefixes as kind of separate words in the vocabulary. So students open there has a separate representation than pupils open there, than scholars open there, right? All of these are separate rows in my n-gram table. And none of these one-hot representations are actually sharing information across each other. So one of the biggest problems of using a one-hot representation is that all words, phrases, etc. are equally dissimilar. So a movie and film, right, we know that they're synonyms, but if you look at their two vectors, their dot product is 0, their vectors are orthogonal. They're no less dissimilar to each other than they are to random other words, right? Like any of the other words in my vocabulary, I, hate, love, and the, right? All words are equally dissimilar in this vector space. So I can't really share any information on occurrences of movie and occurrences of film. They don't influence each other. So what we want is a representation space in which all of these semantically similar units of text also have similar representations. So we're going to move from these one-hot vectors to low-dimensional real valued vectors, so not just zeros and ones. And this is where neural networks enter the picture. So in a neural language model, I'm going to take my prefix and then I'm going to encode it into these real valued low dimensional vectors. And then I'm going to train a classifier to predict the next word from the representation that my model has learned of this prefix. So in this setting, I'm no longer just counting all occurrences of students open there, right? Instead, I'm actually learning a function to transform this prefix into a vector. And then I'm learning a classifier to predict a word from this low dimensional representation. So this is the shift from count-based to prediction-based models, which really kind of started with, at least in modern NLP, with word2vec, which we're not covering here, and now has kind of infused the rest of the research community. So at a high level in this lecture, we're going to be focusing on the forward pass of these models, which means we're just going to assume we have the parameters of a neural language model, an existing language model, and we're going to go through how we go from the raw text students open there to the prediction of the next word books. In the next lecture, we're actually going to talk about how we train these models. So this is the backward pass, how given a training data set, we're going to estimate the parameters of our neural network model using the backpropagation algorithm. And our training objective is also going to use maximum likelihood. We're going to maximize the probability of our training data conditioned on the observed prefixes and the parameters of our model. Okay. So let's start with words, right? We talked about these one-hot representations, but now we're no longer going to be using those because, as we discussed, they have many issues. So we're instead going to be representing words with low-dimensional vectors called embeddings. And here I should clarify that we are representing word types as vectors. So every word type in your vocabulary is associated with a separate vector. So here the word king might have, this 4-dimensional representation. This is just an example. In practice, the dimensionalities of these embeddings kind of ranges from I don't know, maybe 50 to 1,000 or even more than that dimensions. But it's usually much smaller, maybe an order of magnitude or two smaller than the size of your vocabulary, right, which is the dimension of a one-hot representation. And these are some examples from the original Word-Devec paper, which essentially introduced this concept in a predict-based learning framework, where we see that words that are semantically similar, so king and queen, walking and man and woman, they are also close to each other in this vector space, and they share certain directions in this vector space, right? So the relation of gender here is captured in the vector space by the direction and distance of man and woman from each other. There's also syntactic similarity that these words, the word embeddings exhibit. So walking and walked, right? They have the same stem. If you remember the linguistic level of morphology that we talked about in the beginning of the first video of this class. Here, these are just two different tenses of the stem word walk, and we see that the same relationship in this vector space holds for swimming and swam. Finally, there's country and capital relations that you can see are kind of consistent for different countries and their capitals. So these are all just plots showing that if you're able to learn powerful word embeddings, then you can capture all sorts of semantic and syntactic similarities and stuff like world knowledge in the vector space. And so this will enable us to share information between prefixes that contain different word types, but share some semantics or even syntactic similarities. Okay, so we're going to start with word embeddings, right? So for this prefix students open there, I associate each of these words with their corresponding word embedding. But then we get to this process of composition, right? For these kinds of models, I want a way of taking the sequence of 3 word embeddings and transforming them into a single vector that I can use for this classification problem of predicting the next word. Right, so my goal is to predict, say, books. Maybe books is the word that appeared in my training data set. And I'm going to predict this from the composed representation. So there are a lot of new concepts here that I'm kind of going through pretty quickly. So I just want to break this down into smaller pieces. So let's start with how this prediction process happens. Right, so now I'm given this composed vector that represents the meaning, the semantics, the syntactic structure, etc. of this prefix students open there. It's all been squashed together into this low-dimensional, real-valued vector by this neural network function. So let's ignore that neural network component for the moment and just look at how we can go from one of these vectors to an actual prediction of a word. So this is a very important concept that you'll see over and over again throughout this class, is that we're going to use a softmax layer to do this. And at a high level, what this does is it takes as input a vector, and it outputs a probability distribution over the entire vocabulary, or output space for a more general task. So let's look at that in a little more detail. In this particular example, if I have my low D representation of students open there, so let's say it's this like 3-dimensional vector here, what I want is a probability distribution over the entire vocabulary, right? So however many word types there are in my vocabulary. And if this is a prefix that I'm observing at test time, I of course want the probabilities to be pretty reasonable, right? So maybe a high probability to something like books and laptops, and low probabilities to words that just don't make sense within this this context. Okay, and this is how we're going to be estimating these conditional probabilities in this neural language model framework. So this conditional probability of any word, W sub I, given the vector for students open there, is going to be estimated through this learned neural language model. So we're no longer just counting and normalizing, right? We're actually learning a model that predicts this distribution. Okay, so let's go into a little more detail. Let's say that our output vocabulary in this example consists of just 4 words: books, houses, lamps, and stamps. So, of course, books is like the only plausible continuation of this this prefix. I guess maybe houses is plausible in some situations, but anyway, so this is just a simplified example. So we're going to start with our low-dimensional representation of students open there. And what we want is to get a probability distribution over the 4 words in our output vocabulary. So note that to be a valid, well-formed probability distribution, all the elements of this vector need to sum to 1, and they all need to be positive, right? So between 0 and 1. So every dimension, each dimension of this vector is associated with a particular word in my output vocabulary. So you can interpret this as a model that produced this distribution is giving a 60% probability to books being the next word, a 20% probability of houses, and so on. Okay, so let's get into an actual specific example. So instead of just showing you this picture of a vector, let's use this actual example of a 3-dimensional real-valued vector, -2.3, 0.9, and 5.4. This is going to be the sample representation of my prefix students open there, and we're going to call it X in our notation. So this is a vector. Okay, and let's say we also have this weight matrix W. So we'll get into that in a bit. But if you recall, our output vocabulary has 4 words, and this is a 3-dimensional vector. So we need some way of getting from a 3-dimensional vector to a 4-dimensional vector, which is a probability distribution like we saw on the previous slide. So that's where this weight matrix comes in. It's essentially used to project this 3-dimensional vector into a 4-dimensional space. And then we're going to use another function to convert the resulting 4-dimensional vector into a probability distribution. So how do we do this projection? Well, okay, sorry. First, let us look at the specifics of what each dimension in this vector corresponds to, and also we'll look at what the rows of this weight matrix intuitively mean. So you can kind of interpret each dimension of this vector X as a different feature of the prefix. Remember, students open there in our example. This is not exactly analogous to if you're familiar with feature-based like logistic regression or log linear models, where you manually define features ahead of time and then assign them to specific training or test examples. This is not exactly the same, because in this scenario, the features are actually learned. So these features, the values in this vector are, if you remember, the output of our neural composition function. But you can intuitively think of them as encoding different like linguistic properties of the prefix. And similarly, the weight matrix, if you look at that more closely, you'll see that it's a 4x3 matrix, right? 4 rows, 3 columns, and each row corresponds to the weights of each of these features for a particular word in the output vocabulary. So this row corresponds to books, this row corresponds to houses, this one to lamps, and this one to stamps. And you can kind of interpret, I guess I can't highlight just a single cell here, but like this 1.2, this 0.2, 8.9, 4.5, these are the weights of the first dimension of the prefix representation for each of the words in the output vocabulary. So, for example, if this was negative 2.3, it looks like, for lamps, this is assigning kind of high importance to this feature versus something like houses, where this value is fairly low. Now, you can't necessarily interpret these things in this way. I'm just giving you some intuition, but certainly the rows here correspond to specific words in your output vocabulary. So that'll be a little more clear when we go over the actual computation. But at a high level, the dimensions of the prefix representation correspond to features, and the rows of the weight matrix correspond to feature weights for a particular word in the output vocabulary. Oh, let me move this thing down here. Right, so just as another caution, these intuitions we can't easily interpret these features in the way that I've described here. Like we can't say that, the second dimension of this X vector corresponds to a particular linguistic property. We'll get into this more when we talk about linguistic probe tasks, which are specifically designed to kind of investigate what linguistic properties are encoded by these vectors. But I think it's a reasonable intuition for people just getting started. Okay, so we talked about how we want to get from this 3-dimensional vector to an eventual 4-dimensional vector, which is going to form our probability distribution of the next word. So if I take this matrix vector product Wx, get a 4-dimensional vector, right? Because I've multiplied this 4x3 weight matrix with this 3-dimensional vector. So the resulting matrix vector product is 4 dimensions. But let's look more closely at what this actually means to kind of connect with the intuition from the previous slide. I know that was probably pretty confusing. But let's look at how we got this 1.8 number. So I'm multiplying each value in the first row with the corresponding dimension in my prefix representation, right? So I get 1.2 times negative 2.3, right? This is the feature weight for the first dimension of the prefix representation. Similarly, I add that to minus 0.3 times 0.9 and 0.9 times 5.4. And so this is essentially just the dot product of the first row in this weight matrix with the prefix representation. And that's how I get the first dimension of this matrix vector product. So similarly, minus 11.9 results from doing the same thing with the second row of this weight matrix, and so on. So this hopefully clarifies why I referred to each row here as associated with a particular word in the output vocabulary, right? You can see that we're using the first row here only to compute the value of the first dimension in this matrix vector product. And if you remember, the first dimension here is going to eventually be associated with the probability of the word books. Okay, so if you look at this matrix vector product here, you'll notice that it is not a well-formed, valid probability distribution, right? the numbers here do not add up to 1. They have negative numbers, and so I need to still do something to get to a probability distribution. Okay. And this is where the softmax function comes into play. So this is a very important function that you should make sure to understand thoroughly, because we'll see it over and over again through the rest of the semester. It occurs in things like attention mechanisms and other things as well that we'll be covering. So if you look at this function, it takes as input a vector x, and all it does is exponentiate in the numerator. So this is going to make all of the values positive, and then it's going to normalize by the sum of this vector, the exponentiated vector. So that normalization step makes the sum of this vector, of all the elements in the vector, equal to 1. So this function accomplishes both of our goals, right? We get a vector where all the elements are positive, and also all the elements sum to 1. Okay, so in this example, I kind of chopped a little bit off these numbers to make them more reasonable. In the previous case here, we had negative 11.9 and 12.9. You wouldn't see these numbers in a normal neural language model. They're fairly large, and these extreme values dominate the softmax computation. So I made them a little more reasonable just for sake of example here. So if you say the matrix vector product is equal to this vector, applying the softmax function to this matrix vector product gives us the following vector, where the first dimension is 0.24, so 24% probability for the word books, 0.006 probability for the next word, whatever that was, houses, 0.73 probability to stamps, and 0.02 to lamps. So obviously this is not a great prediction, right? It's predicting 73% probability of observing lamps given students open there, but this is just an example. So in the next video, we're going to talk about how, if we have a model that's predicting something wrong like this, we can adjust its parameters. And the parameters of this model that we've seen so far are these weights in this weight matrix here. How can we adjust those parameters to make the resulting prediction put more probability mass on the probability for books and less on these other words? All right, so this was the first step of the, sorry, we were working our way backwards. So this is actually the last step of neural language modeling, how we go from a vectorized representation of our prefix to a prediction of the conditional probability distribution of the next word. So just to sum up, if we're given such a representation of a prefix, we'll call it x. We do the following two steps to get converted to this probability distribution. We first project it to a v-dimensional vector, where v is the number of word types in our vocabulary, using a matrix vector product, as we saw on the previous slides. So you might see this called as a linear layer. This is a PyTorch terminology, or a feed-forward layer, or fully connected layer. There are many different names for this projection step, but here we're in all cases we're just doing a matrix vector product. And the goal is to transform this representation that we have as input to a desired output space. So in this case, we want a v-dimensional output space. And the second step, once we get this vector, is to simply just apply the softmax function to get it into a probability distribution. Okay, so now that we've covered how we actually get a predicted probability distribution given a representation of the prefix, now let's turn our focus to how do we compute this single representation of the prefix in the first place. So as mentioned before, we're going to have a neural network that acts as a composition function. So it takes as input a sequence of word embeddings. So here, the embedding for students, followed by the embedding for open, followed by the embedding for there, and squashes it down into a single vector. So there's many different ways you can implement this neural network. In your homework, we look at element-wise addition, which means given these three vector representations, I'm just going to add them up element-wise. So I'm going to add the first dimension of each of these vectors to get the first dimension of my composed representation, then add up the second dimension of each of the three vectors to get the second dimension, and so on. So this is one of the simplest composition functions, element-wise addition. You can also imagine things like multiplication or max or something like that. Average is also a popular choice. Yeah, this is just one way of composing these functions, right? So the problem with doing something like element-wise addition is that we ignore the order of the words in the sequence, right? So my representation for this prefix students opened there is going to be the same as the representation for opened their students or their students opened, or any permutation of these words. So it doesn't take into account the order of the words in the prefix, which we obviously know is critical, right? It conveys a lot of semantic and syntactic meaning. And so we want to be able to model the left to right order of these words. So how can we get around that problem? Well, there are many different ways we can do this. A simple approach is concatenation. So we'll look at this in more depth in a bit, but essentially I can just concatenate these three embeddings together, and that'll give me, if you assume each of these is a three-dimensional vector, my composed representation will be nine-dimensional. So this has some issues that we'll get into later. And those issues kind of motivate the next class of function, which are more complicated. So we have feed-forward neural networks, convolutional neural networks, recurrent neural networks, and finally transformers. The latter class of model, the transformer, has become the most popular neural network architecture in NLP. And so our focus is going to be on transformer-based architectures for most of this semester. In this lecture, we'll go over concatenation combined with feed-forward neural networks, and we'll also look into recurrent neural networks. Next week, after we've covered backpropagation, we will start looking at the transformer attention mechanisms, and then finally get to the overall transfer learning paradigm and specific implementations of that have been proposed over the past couple of years. That was random roadmap in the middle of the video. Okay, so let's look first at concatenation. So we know that concatenation at least preserves the order of the words in the prefix, right? In contrast to element-wise addition or mean pooling. So let's say we have our prefix, right? The students open there. We'll actually treat this in a similar way to the n-gram models, in that we're going to consider a fixed window for our prefix. So if we had the students open there occurring in the context of the larger piece of text, as the proctor started the clock, the students opened their blank, we're going to just discard parts of that are outside our fixed window. So in this case, our window is just 4 words. Later, we'll look at models that don't have this limitation and can theoretically handle unlimited context, although practically that's not true. Okay, and we'll call this a fixed window neural language model. This model was proposed initially by Yoshua Bengio in 2003. It's one of the readings that are on the website for this week's lectures, so you should definitely check that out. Okay, so how does it work? We'll start with our word embeddings for each of the 4 words in the prefix. Right, so in this visualization, each word embedding is 4 dimensions. So each of these 4 circles corresponds to 1 word embedding. And the first step is just concatenate them together. So if each word embedding is 4 dimensions, our concatenated representation, our x vector here, is 16 dimensions. Now, an important concept in any form of deep neural networks is to add a nonlinear function into the mix. And so we're going to call this a hidden layer in our terminology. But essentially, it's a function that takes as input this concatenated representation and produces a new vector as output. And we've applied a nonlinearity in the form of this function f, as well as a projection matrix, a linear layer. You can see here we have our matrix vector product like we saw before. So if you look at the dimensionality of this new vector here, it's actually 12 dimensions, right? Not 16 dimensions. So we've projected it down to a lower dimensional space than the initial concatenated representation. So you might ask, what is the purpose of this nonlinearity f, right? And what is the purpose of this whole hidden layer? Why can't I just directly apply my softmax layer to this concatenated representation? There's nothing preventing you from just discarding this hidden layer and immediately proceeding with a softmax layer. But the point of adding these nonlinearities is to be able to model nonlinear relationships between the input and the output. So this is kind of hard to think about in the context of language modeling, but a classic problem that kind of motivates the inclusion of these nonlinearities is the XOR problem. And so you can read more about this. Maybe I'll put a link to it on the schedule, but essentially these nonlinear functions allow for much greater representational capacity and modeling of much more complex relationships than a fully linear network. So the state of the art in these kinds of models actually contains stacked layers of these nonlinear projections. So each one of these layers is just increasing the complexity and the types of relationships that the model can handle. And so what do I mean by a nonlinear function? So if you look today at the most popular choices, probably the most commonly used one is the rectified linear unit, or ReLU. So this one is very straightforward. The function is just ReLU of x, where x is a vector, is the max of 0 and x. And this is applied element-wise. So basically, any element of a vector that is negative gets converted to 0. Otherwise, it remains the same. It's an identity function. Other choices were popular before this, such as a tanh and sigmoid. They have issues with gradient saturation that will make more sense after we get into the next lecture. But yeah, there is a lot of research on different types of nonlinear activation functions. You might hear these referred to as activation functions when you're doing your readings as well. But at the end of the day, there's a couple that are kind of standard that everyone uses without thinking too much about it. And yeah, the ReLU is one of those. Okay, so we took our concatenated representation, we projected it into this hidden space using a linear layer followed by a nonlinearity. The final step is what we just saw before. We apply a softmax layer, right? So it's a softmax function followed by this matrix vector product with the vector is where the vector h here is the output of the hidden layer computation. So we note that we have two different weight matrices here, right? W sub 1 is doing this projection from a 16-dimensional vector to a 12-dimensional vector. And so its dimensionality is 16 by 12, and or 12 by 16, depending on how you set up the computation. Yeah, in this case, 12 by 16. And the dimensionality of this W sub 2 matrix is going to be the size of the vocabulary by 12, right? So when I multiply this matrix by the 12-dimensional vector h, I'm going to get a v-dimensional vector, which is then projected or converted to a probability distribution via the softmax function. Okay, so again, in this lecture, we are not going to look at how exactly we train the parameters W sub 2, W sub 1, and the word embedding C sub 1 through C sub 4. That's what we'll look at in the next lecture, but note that all of these, the parameters of the model are these weight matrices as well as the word embeddings. All of them are learned through this process of predicting the next word on a given training data set. That will hopefully make more sense after you watch the next video. Okay, so let's step back and do some comparisons between this model to our n-gram model from the previous lecture. So first of all, we no longer have the sparsity problem, right? We're not explicitly encoding this count table anymore, right? And we're not enumerating all possible prefixes that could be formed in the vocabulary. The model size is no longer exponential in the order of the model, right? The window size. But the model still has problems, right? It hasn't really addressed this fixed window thing, right? It's still limited to, in this case, the 4 words that immediately follow the current word. And scaling this model to larger windows is kind of problematic because it grows this concatenated representation, right? So if I wanted to include the last 100 words, I'd have to concatenate 100 of these embeddings together. Then that makes this weight matrix get a lot bigger. And importantly, I'm not sharing parameters between across one word and another word, right? All of these get different weights in this weight matrix. And so this can be a challenging optimization problem, right? If I see the word students in position 83 versus 92, do I really want to use a separate weight matrix or separate weights to handle this, or do I want to share weights? So the next model we'll look at the recurrent neural network addresses this problem, and the transformer also has its own way of addressing this problem. But the recurrent neural network is conceptually much simpler to explain, which is why we're going to go into it briefly here. So in this model, we no longer have this condition of including a fixed window. But just for the sake of demonstration, we're going to just look at the same 4-word prefix that we've been looking at to this point. The students open there. So just like before, the first step is to get the embeddings for each of these words. So again, we have these 4-dimensional embeddings, but we're not concatenating them together anymore. The recurrent neural network is interesting because it proceeds in a series of steps. So it processes a single word, the first word first, then it incorporates that representation with the next word. So that's step 2. Then it incorporates that representation of the students with the word opened, and finally the word there. So in this sequential processing, it kind of operates the same way that humans do when they're reading, right? We read left to right. The recurrent neural network also reads or creates these representations left to right. So let's take a look at how that works. We're going to have this same concept of a hidden state, except this equation looks different than it did for the fixed window language model. So you'll immediately notice that there are actually 2 weight matrices here instead of just 1. And we'll look into the actual roles of those in a couple of steps. So we're going to first start with an initial hidden state. So this is what we have before we've seen any words. It's just like our base representation for any sequence. Now, we're going to integrate this representation with the first word of our prefix, the. So this diagram shows that how we're actually applying the 2 weight matrices, W sub H and W sub E, to do this integration step. So W sub H is responsible for projecting the previous hidden state into a new space. And W sub E is responsible for modeling the word embedding of the current time step. So we're going to use this terminology of time steps because this model proceeds sequentially, right? So in the first time step, we are integrating the word the very first word, with the previous hidden state. So if you look at this equation, W sub h, the matrix vector product, is between W sub h and the previous hidden state, which for this time step 1 is h sub 0, the base representation. And we're adding that to the matrix vector product of W sub e, which is this other weight matrix, multiplied by the word embedding at that time step. So the word embedding for the. Then we apply our nonlinearity, right? This f, which could be the rel u, the tan h, or whatever. And then we get h sub t. So in this case, h sub 1, our new hidden state that has incorporated one word of this context. Now that we have this representation, we're going to integrate the next word in the sequence, students. So at time step 2, we're going to do the exact same computation, except the vectors that we're using change. Note that the weight matrices stayed exactly the same. We're using W sub h again and W sub e, but the matrix vector product this time is WH times h sub 1, right? Not h0. And the matrix vector product for this term is W sub e times c sub 2, the word embedding of students, which is the word associated with the current time step, the second time step. So you can see here that we're actually sharing the weight parameters across different words, right? Which we were not doing in the fixed window case, where we had separate weights for every single word in the fixed window. Here we're using the exact same two matrices for every single time step of this prefix, and so our model size is not dependent on the size of the input prefix. You can also see how this formulation allows you to model an arbitrarily long prefix, right? Because I'm just proceeding one word at a time. I'm using the exact same weight matrices, so those are not a function of the time step. And so I can just keep applying this same equation as I get one more word in the prefix. So I can model as long prefix as I want. So here I'm going to integrate the third word opened, and finally the fourth word there. And now this representation, h sub 4, has information about all four words that occurred in the prefix, right? This h sub 4 is a function of every single word embedding in the prefix, as we saw with this recursive equation, right? And so h sub 4 we're going to treat as our representation of this full prefix. So how do we get from h sub 4 to a distribution over our vocabulary? Well, we already have seen this now multiple times, right? I'm going to simply just use a softmax layer with a separate weight matrix at W sub 2 to project this h sub 4 into the vocabulary space. Okay, so one thing that you might want to always, keep in mind is what are the dimensionalities of the different parameters that we're working with here. So we know our word embeddings are 4 dimensions each. And what about these parameters W sub h and W sub e? So in this diagram, the hidden units are also 4 dimensions, right? So W sub h is just a 4 by 4 matrix, right? It's not changing the dimensionality of the vector that is getting multiplied. It's just making it another 4-dimensional vector. Similarly, W sub e is also a 4 by 4 vector, right? The embedding dimensionality and the hidden dimensionality are the same. This doesn't have to be the case. It's just the case in this example. In practice, these numbers do vary and they're treated as hyperparameters. So things that you have to decide beforehand before training the model, things that you might want to optimize by looking at the end performance of your language model. Okay, and what about W sub 2? Well, the vector that this matrix vector product includes is h sub 4, which is a 4-dimensional vector. And so we want to project this 4-dimensional vector into a size v vector, right? Where v is the number of word types in our vocabulary. So W sub 2 in this equation is going to be v by 4. So when you multiply this v by 4 matrix with this 4-dimensional vector, you get this v-dimensional vector, which when we then apply the softmax to it, gives us this probability distribution. Okay, so in this lecture, we've covered the forward pass for a feed-forward neural language model and a recurrent neural language model. I realize that this is a lot of information that's been compressed into one video. I'd highly encourage you to check out some of the readings that have been posted on the website if you're confused, or come to office hours. Myself and the TAs, all of us are very experienced with these kinds of models and can answer your questions, hopefully well enough that you understand whatever confusions you have. Again, next time we're going to be focused on the actual training process of these models. So before we conclude, let's just take a look at what are the advantages of this recurrent setup over the fixed window feed-forward language model that we talked about previously. So we've already gone through a bunch of these, right? We can process any input, any length input, right? Because we're operating left to right in this one word at a time kind of framework. So we don't have to make any preconceived choices as to what the length of the prefix that we can handle is. Our model size is not, it does not depend on the length of the prefix, right? Because we're sharing parameters across the different words of the prefix. Right, so these are the main advantages compared to the model, the fixed window language model we looked at before. Some disadvantages is that this recurrence is slow, especially during training, because well, this will be more clear when we talk about backpropagation, but if you only have an error signal at the output here when you're predicting the next word, the error that you make, right, if the model was assigning a low probability to books and it should have been high, that needs to be propagated through all of the time steps that we observed in the sequence. And if the sequence is long, this computation might be slow. Additionally, like we've talked at length about the theoretical ability of this model to handle long prefixes, but in practice, it really only encodes information about the last, like a small number of words that occurred immediately previous to the word you're trying to predict. So recurrent neural networks have a hard time, at least in the language modeling case, looking beyond, say, 20 to 30 words. You really need to make them deeper, train them on a huge amount of data for them to be able to actually make use of the extended context. But there are a number of optimization challenges with recurrent neural networks, which have kind of shifted researchers over to transformers, which at least during training are much faster to train, more parallelizable, and easier to scale. Okay, so finally, we're, as mentioned before, going to be looking at backpropagation next time. So how we actually train these networks, how we get the parameters, the weight matrices, and the word embeddings. And then you can look out for the transformer architecture coming next week. Okay.